All right. Well, welcome to March. We're finally here, last month of the quarter. So just a couple more weeks to go. Get excited. Um, so our plan today is to continue doing some trig substitution. I'm going to show you a few more examples of that, and then show you how we can use another algebra technique that you learned probably once upon a time called partial fractions. Partial fraction decomposition, how that will help us when we want to do some integrals as well. So another day of trig and algebra, setting up ourselves for easy integrals. All right, so using what we learned in the past to make integration easy. So that's my plan, but let me turn it over to you guys first, because I know there's homework due tonight. What would you guys like to see from the homework sets? Spend a little bit of time. Okay, I don't believe that it's nothing. That never happens with you guys. Everything's going good. Hyperbolics were easy. Oh, there it is. Thanks, Lexi. I could count on you and Chase. So 3.2. Let's see. We got 16 through 18. Okay, and then the setup for the last one on 3.1. Does that happen to be number 11? Oh, we'll go take a look at those. All right. So let me go ahead then and share my screen, and we'll go see what those look like. And I just realized I'm on the wrong class. You guys are not statistics, you're calculus. Is it just me, or are these mornings getting earlier? I swear it feels like they get earlier every day. All right, let's see here. Okay, so let's look at 3.1 first. Maybe brighter each morning, Rigney, but not in my mind. Okay, so real quick, let's look at number 11. So number 11 from 3.1 says a particle moves along a straight line, has a velocity t squared e to the minus 3t. How many meters will it travel during the first t seconds from 0 to t? Okay.
Figure out what they were really asking for, because it's from 0 to t. So I integrated it, but then I didn't know I had a formula, but yeah, I didn't know what to plug in.
So when you integrated, you got a formula with a plus c, right?
Yeah, and then it said like syntax error or something like that.
Okay, so the c ends up being 0 in this case, because what it's asking is how many meters will it travel during the first t seconds. The plus c is telling you the position, right? So that's where we're located. So if you were to take the function that you had with the plus c, that's its position after t seconds. But if you want to know how far it traveled, you have to subtract off where it was at the start. And where it was at the start was c. So you'd end up subtracting that c off. So if you just integrate it, if you just integrate it, but then don't put the plus c, that's actually going to give you the formula for how far it will have traveled during the first t seconds.
Okay, I tried that. I put it in, and I literally my first problem was different. Then my second one was the exact same as the example in the video, and I put in the exact thing they put in the video, like the formula, and it still said I was wrong. Do I subtract c or no c at all?
Well, there shouldn't be a c at all. I'll tell you what, Adam. Let me after class.
Yeah.
After class, let's look at your specific one, and we'll see what the issue is.
Okay.
It could be something as simple as just a parenthesis wrong or something, or who knows, but or it could be on them. So let's look at that specifically, because if you feel like you did it right with the integration, then it's probably something different. So, okay, and then Rigney, I think you said you wanted just to see the setup for the last one. So we're going to find the volume generated by rotating the region bounded by y equals natural log of x, the x-axis, and the vertical line x equals e squared about the x-axis. Okay, let me write this down. All right. All right, let's go to the whiteboard here. So we're looking for the region bounded by y equals natural log of x. So natural log of x does that. The x-axis, and x equals e squared. So somewhere out here is e squared. So we're looking at this region right here, the region bounded by y equals log x, x-axis, and x equals e squared. And we're going to rotate that about the x-axis. All right, so let's remember what we do when we set these suckers up. So we're going to probably want to do this with, well, I mean, we have options. We can do it with slices. So if we were to think about what a representative slice would look like, it would be that, right? Because our shape is going to come up here. And so those slices are going to be circles. If we set it up this way, the volume is going to be the integral of pi times the radius squared. So this is going to be pi times natural log of x squared, right? So that's the slice times its thickness, dx. And then we would integrate that from 1 to e squared, because that's 1, where natural log is equal to 0. So that would be the setup if we did slices. We also could do cylindrical shells if we were so inclined. So there would be an example of one of the cylindrical shells. And for cylindrical shells, you guys remember how we do that? That's the 2 pi RH business. And so if we were going to integrate that thing, we'd integrate 2 pi. The radius is given by the y coordinate. The height, that's e squared minus e to the y. Because this one, if this is y equals natural log of x, if you solve it for x, it's x equals e to the y. So the height of that cylindrical shell is going to go from e squared down to e to the y. So there's our 2 pi RH, and then we need a dy. And then the bounds on this integral, the y values that cylinders take on, go from 0 up to this guy, which is going to be 2. Because if we're at e squared, that's y equals 2. So this would be shells. So for this volume, you actually have your choice of which one you want to do. I definitely see one I would prefer in terms of the integral, and that's the shell method, because one of them we're integrating just y. So we've got 2 pi e squared, that's all constant, so that'll be fast and easy. And the other one is y e to the y, and that will be a integration by parts. The other one, if we try to do natural log of x quantity squared, we probably need to do that by parts as well. But that's going to get really gnarly because a u sub isn't going to be very useful. If you let u equal natural log of x, actually that wouldn't be terrible, because then the du would give you a 1 over x. You could replace that with x equals e to the u and then do integration by parts. So this one would be a u sub followed by integration by parts. So it doesn't really matter which one you do, but I would probably pick shells. Anyway, so is that good enough there, Rigney?
Yeah, I appreciate that. I was just trying to figure out like if this is just a review question or if it was that we were going to use this integration by parts on this problem. So
yeah,
I see how to do that now.
Yeah, integration by parts is going to come in either way. Let me real quick for this other one, instead of just talking through it. If you did say u equal natural log of x, then du is 1 over x dx. So this would turn into u squared times x du. And so we'd still have to replace that x, but if we just run the, convert this into exponential form, that becomes e to the u. So this one would actually turn into a integral of u squared e to the u, which again is going to require integration by parts. It's just going to be one that requires 2 steps. So, all right, there then is that one from 3.1. So let's go take a look at the ones from 3.2 real quick. All right. Woohoo, trig integrals. And for those of you who know me, that really is a woohoo. I love trig. So elegant, so useful, so despised by most students. All right, so let's look at 16 here. So 16, particle moves in a straight line with a velocity given by this. Find its position function if f of 0 equals 0. Okay, so this is the good old same old. We're given velocity. We want to find position. So we're going to need to integrate. All right, so let's come back here. I'm going to clear all that stuff out. So we've got v equals sine of omega t cosine to the 9th of omega t. Okay, so because of this form, what do you want to do to find the position? If we're going to integrate sine of omega t cosine to the 9th, we're going to do some sort of a substitution. What substitution do you want to do here? What's going to work? What do you do with sine and cosines? What do you look for? All right, so Alexi's suggesting using cosine for our u, and I definitely agree. Now what you want to look for are the powers on these, and you need to have, well, you don't need, if you have one that's odd, that's going to be, that's good because you can save one of those for your du. Since they're both odd, we actually can use either, but the far superior choice is to let u equal cosine of omega t. If we had gone with u equals sine omega t, we could have used one of the cosines as the du, but then we would have had to change all that cosine to the 8th, get that in terms of sine, and that's going to be way too much. So du then is going to be minus omega sine of omega t from the chain rule. And when we change this, we're going to get minus 1 over omega times u to the 9th du. So that'll be minus 1 over omega u to the 10 over 10 plus c. So we'll go ahead and put that back in. And we're there. All right, so then the last thing they told us that at t equals 0, our position equals 0. So we need to put that in to find our c. So we're going to get 0 is equal to minus 1 over omega times cosine to the 10th of 0. Well, cosine of 0 is 1. So that actually tells us that c is equal to 1 over omega. So don't forget, we can actually find that c when we're given some more information. All right, so this one was actually pretty quick. Just good old u equals cosine, and we were done. All right, so how's that looking? Okay for that one? So let's go see what 17 has in store for us. Ooh, find the length of the curve, natural log of cosecant of x from pi over 4 to pi over 2. Oh, that one looks fun. All right. So this one, we have to remember how to do arc length. So quiz for class, how do you find arc length? What do we integrate? Does anyone even remember what we do for arc length? There's one that's got a square root in it. And it was 1 plus f prime of x squared. So given any function, this is how we can get its arc length. So for this particular one, we know that f of x was, right, natural log of cosecant. So let's get its derivative. All right, so the bottom gets what's inside the natural log. And then the top gets the derivative of cosecant. which you guys hopefully all remember is negative cosecant cotangent. So the cosecants cancel and we just get negative cotangent. So our arc length then, we were going from pi over 4 to pi over 2, I recall. Maybe the square root of 1 plus negative cotangent squared. So this is the square root of 1 plus cotangent squared. All right, so that's just using what we know about how to find arc length, brings us here. So now the question is, can we simplify that? And the answer should be a resounding yes. Because we got some identities. If you use the Pythagorean identity, right? Remember, there's the main form, which is the sine squared plus cosine squared equals 1. But there's also a form that's 1 plus cotangent squared is equal to cosecant squared. And yes, I would expect that you would recognize that and go, oh, there's a Pythagorean identity that involves that. If you don't see that, you need to bone up on your identities. So square root of cosecant squared is just cosecant. So this arc length formula ends up being pretty nice. It's just the integral of cosecant. All right, so you got to integrate cosecant. We have a formula for it, or you can use integration by parts, where you let u equal your cosecant and go from there. Or you can turn it into a 1 over a sine, and then do a little bit of u sub or what have you. But at this point, I'm going to turn you loose because that's fast and easy. All right, so okay for that one. Okay, so let's go look at the last one here, number 18. This is another one we'll go ahead and get set up. Find the volume generated by revolving the curve y equals cosine of 2x about the axis, about the x-axis from 0 to pi over 4. All right, so this is going to be kind of similar to that other one that came from the u sub. We just have a different function, so let's see what that guy looks like once we draw it out and everything. So we'll clear all that stuff again. Okay, so we've got cosine of 2x, which just looks like cosine, just faster. And we're going from 0 to pi over 4. So 0, of course, is right here. And so then pi over 4 is going to be the peak of this thing. Because the fact that we've got a 2 in there, right? We've got the cosine of 2x. That cuts our period in half. So we repeat every pi instead of every 2 pi. So pi over 4 brings us there. All right, so that's where we are. So we're looking at this region that we're rotating about the x-axis. So again, we have options. We can either do this with disks or with shells. Let me go ahead and write them both out. So if we go with the disk method, the volume is going to be the integral from 0 to pi over 4, pi times our function squared, so cosine squared 2x dx, because one of those little disks looks like that. There's our r is given by the function value. So if you do it the disk method, it looks like that. If we go to the washer method, or sorry, not washer, cylindrical shell method, there's an example of one of them. Okay, so now we're going to have 2 pi r times the height of these things. Okay, well, the height's going to be pi over 4 minus, I got to solve this for x. So it'd be cosine inverse of y over 2 dy. The r is actually a y value. And then our y's are going to go from 0 to 1. Well, I don't know about you, but there's definitely one of these that I would use. And that's the disk method. Inverse shell, or the shell, as soon as you get that inverse cosine, I don't want to bother with integrating inverse cosine. Plus the disk method, I mean, that's pretty fast. Cosine squared. If we run with that, I'll give you the next step. Because what do we do when we have only even powers? What's the trick with that? Do you remember what we do when we have just even powers? This is when we use the power reduction identity. So it's going to be, for some reason I'm not drawing here. There we go. 1/2 times 1 plus the cosine of 2 theta. So cosine of 4x. So you double the angle, and then you end up with the division by 2. But now this is going to be fast. The integral of 1 is x. The integral of cosine of 4x, that's going to be a 1/4 sine of 4x. Plug in your bounds. You're good to go. So again, volumes have a couple of choices of how to do it. One is definitely better than the other. We kind of saw that too with the other one. I think the shells was a little bit better than using the disks with the one with the natural log, but they're both doable. It's just a question of what you want to do. All right. So hopefully that's a good little shove with some of these. And yeah, the stuff that we've talked about before, those applications, you still need to know how to do them. So things like arc length and all that. All right, well, then now that we've kind of done a little bit of review there, let's keep talking trig substitution. All right, so I'm going to hop up to the whiteboard. We'll do a few more examples and then move on to partial fraction decomposition. So I'll be right back. All right, so last time we were talking about trig substitution. And trig substitution really comes in handy when we have certain forms for our integral. And these were the forms where we wanted to use trig sub. All right, so the first one was the form square root of a squared minus x squared. And for this one, the substitution that we made was we went with x is equal to a sine theta. So if you're in this form, you let x equal a sine theta, things are going to work out pretty well. The second form was where we have the square root of a squared plus x squared. And for that one, the substitution you want to use is x equals a tangent of theta. And then the third choice was where we have the difference of squares, but in reverse. Right down here, so I'm under the glare. We have x squared minus a squared. And that one, we wanted to let x equal a secant of theta. So really, the key to knowing, do I want to try trig sub, is if you've got a square root with squares in it. Sum or difference. Because those naturally lead to trig sub being a good technique. Okay, so that's how you recognize when you want to do it. So let's kind of remind ourselves what the process is. All right, you're going to do the substitution. So you're going to differentiate, you're going to put in for the dx and all that. Right? So you're going to do the substitution. What it's going to turn into is a trig integral. All right, so then we go ahead and integrate that. So we use the techniques that we learned prior. The whole, like, okay, look at the powers. If they're odd, say one of them. If it's secants and tangents, we look for one of each, or two secants to be part of our d. Right? So we have all those techniques, but we integrate that trig integral. And then when we resubstitute, I'm going to put here substitute back. I'm going to put here using the right triangle. Because often what happens is that when we go back to substitute, we're going to need to know one of the other trig functions, or potentially more than one of the other trig functions other than the one that we substituted ourselves. And so that's where we use the right triangle, set up our picture, and get the right ratios. Okay, so that's the process. That's the general process for trig sub. So I think we only did like one example last time. So I wanted to do a couple more today, just so you can kind of see the process and see how it works. And how my little recipe, like what that actually means when we do them. Okay, so this is what we're going to do. We're going to look for these forms, pick the right substitution, and then go for it. All right, so for example, let's try this one. We'll start with this one, kind of a nice little warm up, I guess. It's not terrible. Well, let's try this guy. Let's try to integrate x cubed over the square root of 1 plus x squared. All right, so again, what keys me in on trig sub with this guy is you look at the denominator and there's a sum of squares in that square root. Okay, so the square root with the sum of squares, ooh, trig sub. The alarm bell should go off. Now, since it's a sum of squares in that square root, that suggests that the substitution we use be x equals a times tangent. And since it's 1 squared, this just suggests let's use x equals tangent. All right, so then our dx is secant squared. Derivative of tangent is secant squared. So let's put all this stuff into our integral. So I've got x cubed. That's now tangent cubed. My dx is secant squared. Secant squared d theta. And then I'm dividing by the square root of 1 plus tangent squared. All right, so that was step number 1. Do the substitution. We picked the form based on what this looked like originally. So we picked the x equals tangent theta substitution. And then we fired it all in. So we're going to want to integrate this trig integral, but let's simplify it first. So if we keep going down here, we've got tangent cubed, secant squared, and then on the bottom, 1 plus tangent squared is secant squared. The square root of that is just secant. And so we can do one more step to simplify even a little bit further. We've got the secant that's going to reduce. So let me bring this back up over here. And at this point, what we've got to integrate is the integral of tangent cubed secant. All right, so that's as nice as we're going to be able to make this right now. So we've converted it from this fraction with square root business into just a trig integral. But this is going to be definitely doable. All right, so we've got tangents and secant. So remember what we look for. We either want a secant squared that we can reserve for our du, if we pick tangent, or we want a secant tangent. Well, that's what we're going to do here. Let's strip this apart so that we've got tangent squared times tangent secant. So that suggests doing a u substitution here, where we're going to let u equal secant of theta, because then du is going to be the secant tangent. So this piece right here, we've already used for the du. So now we need to write tangent squared in terms of u. Well, that's where that Pythagorean identity is going to come in handy again. We have that tangent squared plus 1 is equal to secant squared. So tangent squared is secant squared minus 1. So if I change that, this is now going to look like the integral of u squared minus 1 du. and that's going to be fast. All right, but check this out. And sometimes they'll say, you know, you lose the forest for the trees. We're still looking at the details. We kind of lose the big picture. I just want you to look at where we are now, this red integral, and compare that to the integral that we started with. You would pay big money, huge amounts of money, if every question on the final exam was integrate things like u squared minus 1, right? That would make your day. We, using just some algebra and trig, and then no, just some, no, it is just some algebra and trig, turn this horrible looking thing into one of the easiest integrals in the history of integration. That's the power of this. And yes, it's easy for me to say that because I like trig. I don't mind doing trig manipulation. I remember identities. And yeah, that's why we teach you identities. That's why we tell you, hey, pay attention to these. You're going to use them later. Because if you have those tools handy, oh my God, it makes calculus nothing. It makes calculus absolutely nothing. Anyway, so let's finish this off because we're almost there, right? If we integrate that, we're going to get u cubed over 3 minus u plus c. But now we get to start substituting back. All right, so u, remember u is equal to secant of theta. So we'll go ahead and put that back in. So we're going to get secant cubed over 3 minus secant. So there was one layer of our substitution gone. And now we need to substitute in for secant. But this is where that whole triangle business is going to come in. Because here's what we know about theta. We know the tangent of theta is equal to x. So if I draw a right triangle here, there's my theta. I know the tangent is equal to x. So tangent is opposite over hypotenuse, right? If you think of that as x over 1, or sorry, opposite over adjacent. So tangent is x over 1. All right, well, I want secant. Secant is 1 over cosine. So for cosine, I need adjacent over hypotenuse. So I need to get this side right here. Well, that's going to come from the Pythagorean theorem. A squared plus b squared equals c squared. So from that picture right there, I know that the secant of theta is the square root of 1 plus x squared over 1, or the square root of 1 plus x squared. Now I'll plug that back in here. So we end up with our integral, well, eventually now, is equal to the square root of 1 plus x squared cubed over 3 minus the square root of 1 plus x squared. And we'll put a plus c. So we got to this with super easy calculus. The calculus portion of all this was fast, easy, simple. It was all the algebra and trig that got us there. That was the work. And that's why students don't like this. There are a lot of steps, a lot of things that you're supposed to have remembered, but you don't remember. But there you go. All right, so there's another example of trig sub, and we'll do one more, but hopefully this is kind of a good refresher of the steps, and you can see why I said think about what my steps were. Number one was do your do your substitution. So figure out which form you need, right, what form you've got, so then that pushes which thing to substitute. Then after you do that substitution, you do the integral. This one required another substitution, but we got the trig integral. And then we had to substitute back using the right triangle. So that's the general recipe. The specifics are going to change depending upon what the function actually was. Whew. You're going to hate me for this one. Turns out we could have done this with just a regular old U sub. Yeah, go ahead. You can complain bitch mode right now. Check this out. Had we instead recognized this and gone, all right, well, let's try u equaling 1 plus x squared. So then du is 2x dx. If we start substituting this stuff in, we're going to get on the bottom the square root of u. The dx, you're going to get a 1/2 du. One of the x's cancels, and so you're still left with a x squared, because one of them was part of the du. But then you can substitute in for that x squared, because x squared is equal to u minus 1. Come up here. This ends up being the integral of u minus 1 over the square root of u. 1/2 out front. U. Which is also a pretty fast integral. So yeah, we could have gotten away with this one just doing a u substitution from the start. Okay, so why did I do that? Two reasons. One, it was a perfectly good trig substitution form, right? It gave us all the practice. We saw how everything worked. But it also goes to remind you, as we learn more and more techniques, sometimes these more complicated techniques, even though they work, are not the ones that you should pick. Always have in the back of your mind, can I just do a u substitution? Because those are fast and easy, if possible. All right, so always just kind of keep that in the back of your head. See if the form actually reminds you of something else that works before opting for these bigger, harder, more complicated integration techniques. Okay, so now that y'all hate me for doing this to you, let me show you one more, and you're going to hate me for a different reason for this one. Let's try this integral. Let's go with the integral of 1 over the square root of x squared plus 4x. Okay, so before you start getting cute and going, oh, okay, this is clearly one that u sub is going to help us and all that. No, this isn't. U sub isn't anything that's going to help here. But looking at this, you might also go, yeah, but trig sub's not going to work either. Because while we have a square root and we've got some things being added, they're not squares. I mean, one of them is. We got x squared, but the 4x isn't. All right, well, this is where you're going to hate me a little bit. We're going to complete the square. Let's complete the square on the x squared plus 4x. And you'll see that it turns into a form where trig sub will work. So if we've got x squared plus 4x, we need to take 4 and divide it by 2, square it, 4. So I'm going to add 4 and I'm going to subtract 4 at the same time. So this turns into the integral of dx over the square root of x plus 2 squared minus 4. And so by completing the square, you now see that, yeah, we have a difference of squares. So since we have a difference of squares, and the fact that our variable square comes first, this is the one that suggests using secant. But here's how this is going to be a little bit different. Instead of saying x equals, I'm going to want x plus 2 to equal 2 secant of theta. So the secant of theta comes from this form. The 2 in front of the secant comes from the minus 4, right? Think of this as a squared. So a equals 2. That's that piece. And instead of saying I'm going to let x equal this, I'm going to let x plus 2 equal it, because that whole thing that's being squared is where I want to do my substitution. So in reality, the x that we're using, x is equal to 2 secant theta minus 2. So this trig sub is a little bit more robust even than I showed you. It can be used for things that come from, or that turn into the form when you complete the square. All right, well, if that's our x, then our dx will be 2 secant tangent d theta. You'll notice that that minus 2 doesn't really matter because it just goes away when we differentiate anyway. All right, so let's do the substitution and let's just see how it all falls out. We've got our dx, so 2 secant tangent d theta over, okay, so now we've got the square root of 4 secant squared minus 4. So let's see if we can simplify that a little bit. Well, we definitely can. We can pull out the 4 from that square root on the bottom, and it comes out as a 2. Secant squared minus 1 is equal to tangent squared, and the square root of that is just tangent. So that square root on the bottom just becomes 2 tangent theta. We can do all kinds of slashy. And what we're left with is the integral of secant d theta. Cool. That was fast. Good simplification. We're down to just secant. All right. So now we need to remember what the integral of secant is. I don't know if anybody does. It's the natural log of secant plus tangent. We saw that somewhere along the way. All right, so cool. We're there. Now we need to substitute back in. I just want to stop for a second, take stock. Are we good? Kind of seeing where we're going. All right, I'm not hearing any questions. Let's go ahead and finish this guy off. So let's draw the right triangle. So here's a triangle. Theta. And what we know is that the secant of theta, that's equal to x plus 2 over 2. Right? If I take this substitution down here and I solve for secant, give me x plus 2 over 2. So secant is the reciprocal of cosine. So this is hypotenuse over adjacent. So those are those two sides. All right, well, let's look at what we're trying to replace. We need to replace a secant and a tangent. We got secant. We're good to go there. But now we need the tangent of theta as well. So to get the tangent, I need to know this third side. All right, well, let's use the Pythagorean theorem. So we've got 2 squared plus a squared equals x plus 2 squared. So a squared is equal to x squared plus 4x plus 4 minus 4. So a is the square root of x squared plus 4x. All right, so from that, we know tangent, right? Remember we wanted tangent of theta. So the tangent of theta is equal to the square root of x squared plus 4x over 2. Again, opposite over adjacent. All right, and it's those two things that we needed because with our integral, after we did our trig integral, we have to substitute in for secant and tangent. All right, well, let's do that. So here you go. So the integral of what we started with, it's the natural log of secant x plus 2 over 2 plus the tangent square root of x squared plus 4x over 2 plus c. And so there is some simplification we can do with that. Right? Like we can combine these into one fraction. We can then split that apart into 2 logs, and there's stuff we can do. But I'm going to go ahead and leave it there because that's good enough for now. All right, so again, who'd ever thought that with this original integral, that it would have turned into some natural log forms and all that? But we got there by turning it into a relatively easy integral of secant of theta using trig. All right, so what do you guys think about this? Good, bad? Yeah, I think that's pretty honest there. Adam just put it in the chat box. like, I mean, the reality of it is, you think like a mathematician, or what mathematicians want, because we're sore losers, is I just want to be able to do this integral. Now, check the box. Yeah, we can do this integral. It requires lots of steps. And just a little bit of a warning. When you do these, because there are so many steps, it's really easy to make a mistake early on that then carries out. So this is definitely one of those places where you need to be slow and steady. Okay, but follow the process. Start with the initial integral, use its form to push the substitution. Because those substitutions are always going to simplify down when you use the right substitution for the right form. Okay, so start there. Then go slow and steady. A bicycle containing 100 pedals? I don't know about that. It's got one set of pedals, it's just got lots of gears. And you're changing the gears all the time. And as we know, when you're on a bicycle, if you don't change the gears quite right at the right time, it gets crazy difficult, right? I would say if we're going to go with that analogy, this one just got a crazy, crazy sprocket set with tons of gear combinations. And we got to read the terrain right and know, oh, where we're coming up requires this specific set of setup for our gears. Yeah, it's complicated, no doubt about it. But go back and review your identities and practice your algebra. But yeah, this is where all that stuff's kind of coming together. All right, so there's trig sub. It's a great technique when you have certain forms. All right, so I want to start into another integration technique that's used for a completely different kind of form. Right. So think about what we've done so far. We have integration by parts, which is when you got multiplication. We looked at trig integrals. So you now have an idea of what to do when you just have sines and cosines and things like that. We have trig substitution, which works really well for the square root forms of sums and differences squared. So the next technique that I want to show you is really useful when you have fractions, when you have rational functions. Okay, and this technique is called partial fraction decomposition, or partial fractions is what we'll say. Okay, and this technique is for rational expressions. And just remember that rational in this context means fractions of polynomials. Okay, so we're going to use this technique for things like stuff like, what if we have 1 over x to the 4th minus 1, or 2x plus 3 over x cubed minus 3x, or ... Okay, so when we have things that are fractions of polynomials, rational expressions, this is where partial fractions is going to be useful. Now, we have seen some forms of rational expressions that we can integrate. We already have techniques for, right? Like think about like 1 over x squared plus 1. You already know that one. That's just, there are some that we can do use substitutions. We've seen those, right? So some of these we already know how to do. But partial fractions is going to make it so that we can do more of them. And this is a more general process to attack these guys. All right, so to do this, we're going to have to remember partial fraction decomposition. And I say remember because hopefully you've seen it in pre-calc. If you haven't, I'm going to go ahead and kind of give you a little refresher on doing this. Okay, so let me change this to partial fraction decomposition. And I think I just want to, I'm going to work through an example to kind of show you how this works. All right, so suppose that we have this fraction, 3x squared plus 4x plus 7 over x cubed minus 2x squared plus x. All right, and the idea behind this, behind partial fraction decomposition, is to break this into a sum of fractions. We're basically going to do addition and subtraction of fractions backwards. Okay, and the process begins here. You start with the denominator and you factor it. So if we were to take x cubed minus 2x squared plus x, you can factor out an x, which would give us x squared minus 2x plus 1, which then factors to x times x minus 1 times x minus 1. And I'm going to look at this as x minus 1 squared. Now, what this tells me, if the denominator has these factors, it tells me that it came from fractions that have these as their bottoms. So, I kind of split this apart into fractions. I know that one of those fractions could potentially have x on the bottom, because when I get a common denominator, there'll be an x. I also know that there's one that could be an x minus 1 on the bottom. And there's also one that could be x minus 1 squared. Because you can imagine if you were to take fractions of this form, add them together, when you get the common denominator is going to be x times x minus 1 squared, which is what this thing looks like. Okay, so partial fraction decomposition, again, it's you're doing the addition of fractions in reverse. Okay, now what I know is that the tops of these, well, they're going to be just some numbers. I'll call them A, B, and C for right now, right? But it could be like 2 over x plus 3 over x minus 1, right? So those are the things that we're going to try to find. All right, so now that we're here, we're going to actually find what A, B, and C are by putting these back together. And I know this feels really weird. It's like, okay, so we're going to split this apart, but to find out how to split it apart, we're going to put it back together. Yeah, we are. So think about getting a common denominator, getting this common denominator. If I was to build these fractions up, I would get A times x minus 1 squared plus B times x minus 1 plus C times x. So I'm doing that whole trick of I'm multiplying each of the fractions by the missing pieces of the common denominator, right? This first one doesn't have any of the x minus 1s, so I have to multiply the top by x minus 1 squared. The B, this middle one, is missing one of the x minus 1s and an x. And then the last one was missing the x. All right, so if I were to split it apart and then put it back together, it'll look like this. But what this allows me to do now is actually equate the tops. I know that 3x squared plus 4x plus 7 is going to equal a times x minus 1 squared plus bx times x minus 1 plus cx. I just took the top of each of these and I set them equal to each other. Okay, so now I have two ways of finding A, B, and C, and I'm going to show you both of them. Okay, the first one is to multiply this all out and group like terms. So if I were to do that, so let's say I FOIL out, right? I distribute all that good stuff. If we look at the x squareds, I'm going to get an ax squared from this piece and a bx squared from the middle piece. So adding those together, I get a plus b times x squared. For my x's, I'm going to get a minus 2x from the OI part of FOIL. So minus 2 times a. I have a minus 1b, so minus b, and then plus c. So those are all my x's. And then in terms of my constants, there's only going to be the 1 from this square times a plus a. And this is going to give me a system of equations. I know that a plus b is going to equal 3. Because those are the coefficients on the x squareds. I know that minus 2a minus b plus c is going to equal 4. Because those are the coefficients on my x's. And then lastly, I'm going to know that a equals 7. Because those are my constants. So I've got a system of equations that I can now solve. This is actually going to be pretty fast. If a is 7, then over here that makes b equal minus 4. And then I can put those in here, and I think that makes c equal 14, but don't quote me on that. I'm just like a total guess. Not really. 18. Yeah, I think that's 18. Anyway. So there we can find our A, B, and C. So this is one method that you can use. Distribute out, group like terms, create your system. It's not my preferred method. I'm going to show you another method that I like better that I'm going to kind of push you towards. But if you like this method, go for it. All right, so here's another option. Instead of distributing and doing all the algebra, what we can do alternatively, and that's what I'm going to do at this point, is I'm going to plug numbers in. I'm going to plug numbers in for x, because if these two things are equal, they're still going to be equal when we choose our x values. But I'm going to be smart about how I choose my x values. I'm going to have to plug in 3 different x values to get my 3 different letters. But the x values I'm going to choose are ones that make these denominators 0. Because they make these factors 0, which really speeds up the process. All right, so here's how I'm going to do this alternatively. I'm going to plug in some numbers. So I'm going to start with x equals 0. I tend to like to plug in 0 anyway, but watch what happens when I plug in 0. On the left, I get just 7, right? So 0 plus 0 plus 7. On the right, check out what happens. I'm going to get a times -1 squared. I'm going to get b times 0 times -1. That's 0. And then c times 0 is 0. Well, lo and behold, hey, look, a is equal to 7. We saw that the other way too. But there's a equals 7. But notice I didn't do a touch of algebra here. No algebra, just arithmetic. I have plugged in a number. All right, now the next one I'm going to plug in is I'm going to plug in 1. 1's another nice number to plug in general. But watch what happens here. So I'm going to get 3 plus 4 plus 7. That's 14. Now on the other side, when I plug in 1, x minus 1 is going to turn into 0. So I get 0a plus 0b plus 1c. Cool. C is equal to 14. Again, no algebra, just arithmetic. And I think that's what I told you C was equal to. I hope. We can go back and watch the video and see if I was right. Okay, so that's C. So I already have 2 of my values. Now I got to get another one. I have to choose some other number to plug in, and I don't really have a good choice in terms of making the factors equal 0. So I'm just going to pick something relatively nice. I'm going to try x equals -1, because that doesn't seem like that's too terrible. If I plug in -1, I'm going to get 3 minus 4 plus 7. I think that's 6. On the other side, I'm going to get -2 squared, which is 4, so 4a. -1 times -2 is a +2, a +2b, and then -1c. All right, well, this one I need to solve for b, but I already know some of the values, right? I know a is equal to 7. I know c is equal to 14. So I can fire those in there. So I get 6 equals 28 plus 2b minus 14. And if you just do a little bit of arithmetic algebra stuff there, you get b is equal to -4. Which were the same numbers that we found the other way. All right, so I'm a big fan of doing it this way. But we're still not done. Now we get to put those a, b, and c back into this. All right, so we had a over x. Well, a is 7. We have b over x minus 1. B is -4. So I'll put the negative out front, make it a subtraction. 4 over x minus 1. And then c was 14. So we have 14 over x minus 1 squared. All right, so we just did partial fraction decomposition. And I know I just threw a lot at you. We'll definitely talk more about it. But what we did is we took this ugly looking fraction and we broke it into pieces that are smaller and nicer. All right. So why the hell did we even do this? Like, it seems like, it doesn't seem like, I was going to say, it seems like a lot of algebra, right? But there's a lot of this before. So Alexi, should you have seen this before? Hopefully you saw this at some point in pre-calc. If you haven't, don't worry about it, because I am going to go through the steps. I'm going to tell you what kind of patterns you're looking for and what the process is. All right. So I know right now it's probably like you're slamming into the wall. I'll walk you through it a little bit more as we go. But I'm sorry to hear that you haven't seen this before, because it's an awesome algebra technique that's super useful here. But let me show you, like, why do we even care about it? What is the point? Well, remember what I said was we're going to try to integrate these kinds of things. So let's put an integral on here real fast. All right, so this is the horrible thing, a little dx on there, that we're trying to integrate. Instead, if we recognize that we can do partial fraction decomposition, it turns into this thing. I can do each of these integrals separately, and they're all pretty fast. Like, check this out. So the 7 over x, that's 7 natural logs of x. The 4 over x minus 1, that's minus 4 natural logs of x minus 1. For this last one, if you just do a u substitution, this turns into an integral of 14 over u squared. So that becomes a minus 14 over x minus 1. So by doing all this partial fraction stuff at the start, turning it into a sum of smaller fractions, some are different smaller fractions, gives us things that are much easier to integrate. Okay, so this process is going to work for rational functions. When you've got rational functions, if you can split it apart like this, it turns the integration into easy integral. All right, so let's back up and let's just talk about what the process is for partial fraction decomposition. Let me give you the recipe, right? We like to have the recipe. We like the process, all right? And so here's what you're going to do when you do partial fraction decomposition. Here are the actual steps, okay? The first thing you want to do is you want to factor the denominator. So given the denominator of your fraction, factor it. Factor it all the way. Okay. Once it's factored, this is when we start creating our fractions, the smaller fractions, all right? Because those smaller fractions get these factors. So step number 2 is going to be create the, I'm going to call them building block fractions. So we're going to make the ones that we add together to create the original one. Okay, now in this, with this creating the building block fractions, I want to give you some more details. Okay, so here are just some things to know. All right, so linear factors, x minus 2, 2x plus 1, right? Things that just have x, no x squared. Linear factors get constants on top. So if you go back and you look at that example we just did, the factors we had were x and x minus 1. So since those were linear, I just put constants on top, a, b, and c. All right, so linear factors get constants. Quadratic factors so x squared plus 1, things like that. Quadratic factors get linear functions on top. Now, I didn't show you one of those, so we will see those in subsequent examples. But if you got a quadratic factor, you have to put a linear on top, ax plus b, cx plus d, whatever. Okay, so those are two things. And then the other important thing is that when you get a repeated factor, and we had that with the last one, the one that I just showed you. Remember how we had x minus 1 squared, x minus 1 showed up twice. Repeated factors get multiple fractions. And I'm going to put here as many as the multiplicity. So multiplicity is just a real fancy name for how many times that factor showed up. So think about that one that we did, that we started with, that had the x minus 1 squared on the bottom. Because it was squared, there were two fractions. There was one that was just x minus 1 on the bottom. The other one was x minus 1 squared. Had it been cubed, there would have been 3. There would have been an x minus 1, x minus 1 squared, x minus 1 cubed. If we had had, say, an x to the 5th, 1 over x, or over x squared, x cubed, x to the 4th, x to the 5th. Okay, so there's always going to be 1 for each of the powers up to the multiplicity. All right, so that's how we create our building block fraction. Okay, so then, I apologize because this is lots of steps, so I have to erase the earlier ones. So we factored the denominator, and we create the building block fractions. Then what you're going to do, step 3, is put these generic building blocks back together. So you're going to add them together, kind of like what we just did, where you go with the, let's get our common denominator, build it up, blah, blah, blah. Okay. And then at this point, you're going to solve for the unknowns by equating the tops. So you're going to take the tops of the original and the one that we pieced together, and you're going to set them equal. So that was when I had my, I don't remember what, 3x plus 4x plus 7 equals a times x minus 1 squared plus b times x minus 1, right? That was taking those tops and equating them. Within this step, you really have two options. All right, so the first one is plug in values. And you're going to plug in as many values as unknowns you've got. Okay. Or you can distribute and then trying to think, relate the coefficients on the various powers. All right, and so that's your other option, which is let's put here distribute and equate coefficients on the powers. So both of those work. I'm a big fan of plugging in numbers. So when we do them together in class, I'm going to plug in. Okay, so at this point, now we've solved for those unknowns. And now we're ready to integrate. So you're going to integrate the decomposed fraction. So many steps to this. And if you go and you look at the one that I did, that I showed you before as your review, which I guess is not a review, but maybe your introduction for some of you. I did all these steps. So if you go back and you look at them, you can see where those steps happen. All right. So I don't think we have enough time for me to actually run through one completely right now. So I'm going to call it for today. And I know that probably after today, you hate calculus, you hate me, you hate everything about pre-calc. You're wishing you had maybe chosen to be a psychology major instead of an engineering major. Okay. Yeah, I know. This is pretty brutal. Like, there's a lot of algebra stuff we're doing right now. But we'll do some more of these. You'll start seeing the process, hopefully. By the time you practice them, you'll get good at what the steps are. But evidently for some of you like Lexi, and she's probably not the only one, says that never seen this before. For those of you who've never seen it before, we'll do some more. It should start making more sense as we start doing it. Okay, so I'm going to go ahead and call it for today. Just want to remind you that there are homeworks that are due tonight. None of this, right? There's none of this. There's not even trig sub. It's just the through trig integral. So make sure you get in and finish those out. And other than that, I hope you guys have a good day, a couple of days, and I'll see you all on Wednesday.